So in summary, what have we talked about in this lecture? Well, we've said that so far, two systems can be compared by analyzing the difference in the means of their performance measures. But depending on what we know about those systems, whether one system has the same variance in its performance measure as the other, whether they're different variances, or whether those systems have been run so that we can't actually say that the outputs are independent, is going to affect how we calculate the variance and degrees of freedom that will go into the statistical analysis, which but before would mean which would go into how we do the t-test, but now would mean which will go into how we construct the confidence interval. And so these confidence intervals are just graphical visualizations of different types of t-test, namely the pooled variance two-sample t-test, the unpooled variance or Welch's two-sample t-test, and the paired difference t-test. But in the end, we get confidence intervals which we can represent the same way regardless of how we calculate whichever t-test we used. And that's another sort of nice thing about the confidence intervals is that once we're in the confidence interval space, we have one way to interpret them is 0 in the confidence interval or not. And so if it's greater than the confidence interval, then we can say that the one system is clearly better than the other. If it's less than the confidence interval, the other system is clearly better than the other. If it's a middle, we can't really say either of those things. Now, once we go to more than two comparisons, so we've got multiple systems, 3 or more systems, and we'd like to compare among those, we can still use pairwise t-tests or confidence intervals to compare every pair of systems, but we have to use a Bonferroni correction to adjust that alpha parameter, that type 1 error rate. So the type 1 error rate for each pairwise comparison is going to be the desired type 1 error rate of the family divided by the number of comparisons. And so when you scale that type 1 error rate down, you're going to start moving the confidence intervals up. So the width is going to go up, and you're going to lose statistical power, but at least you won't be rejecting equality hypotheses. You won't be detecting differences in the family that aren't actually there. Alternatively, we could use an ANOVA instead of this Bonferroni approach, and then that ANOVA basically is you can think of it as like calculating a confidence interval for all of the systems all at once. And so an ANOVA is a generalization of a t-test for more than two groups. And so that ANOVA will tell you just right off the bat in one shot, is there a difference here? And if the ANOVA comes back and says, I can't detect a difference, then very often it's going to have more statistical power. And so we're going to be able to trust the ANOVA more when it says there isn't a difference than when we do a bunch of t-tests with the Bonferroni correction. Now, once you do the ANOVA, if you want to actually rank them and say, okay, well, now that I've detected a difference between groups, which group is better than the other group, that's where we use these post hoc tests like the Tukey test, for example, or Fisher's LSD. Now, if you're interested for a non-parametric, it's the same sort of idea. You can do a non-parametric ANOVA like a Kruskal-Wallis, and your post hoc you can use something like a Dunn's test. So all these things exist for non-parametric as well. And that's kind of another nice thing about having ANOVA in the back of your head is there are frameworks that extend to data that don't fit the normality assumptions that we would normally need in order to use confidence intervals. Now, for simulation, we would like something that not only detects differences among our sims or among our simulation groups, but helps us optimize because we're engineers and we want to pick the best system and do it in a way that doesn't require us to run a lot of different simulations. And so there are these so-called select the best procedures that let us do that. In ARENA, though, you often aren't going to have to worry about all this because you have the process analyzer. So what you can do in ARENA is you can set the process analyzer up with multiple different models and let it do the statistical test for you. And all you need to do is be able to interpret its output, but it will end up making a lot of intelligent decisions for you behind the scenes. And so when you're starting out, it's great to have these tools because they end up doing the stats for you, and you just need to know enough stats to sort of be able to process the outputs that come out of them, but you don't end up having to do the stats yourself. So look for the process analyzer. It's a great shortcut for all of these things because it will make statistically rigorous conclusions from all of your simulation models. All right, extensions. So I've just talked about, just sort of summarized, everything up through the process analyzer for how do we analyze these things. Now, that's just analyzing a set of groups. Now, select the best kind of is the tip of the iceberg of optimizing. So we might have a large number of simulations and we want to effectively do a select the best procedure on that. So we want to then say, like, you might have a wide number of parameter sets, and you want to be able to choose which set of parameters will actually give you the best performance when there might be a million different ways that you could choose those parameter sets. Now, rather than generating a whole lot of different groups and then using the process analyzer to try to sort them out, then you can use a tool like OptQuest, which uses proprietary software algorithms in the background to automate the optimization process. And so OptQuest is pretty cool in that you just give it your model and you give it basically the things that can change your decision variables in the model. And you say, look, I've got these 5 decision variables, and these 3 decision variables vary continuously from in this range, and these 2 other decision variables vary discretely, so they have discrete values, they're categorical. And so I want you to do an experimental design using those, and then test my system however you would like to design the system. OptQuest, again, the software is doing this all for you. And then out of all of that, I want you to tell me which combination of parameters is the best for this simulation model, and it'll do that optimization for you. The design of experiments, the search, sequential sampling, all that, it all does it for you, and it gives you an optimal solution for a simulation model. This is, if you imagine doing this yourself by hand, it should give you the impression that running millions of simulations and then choosing among them in a statistically rigorous way is not trivial. And this is actually an entire field of research. We have faculty at ASU that do this in full time. That this is their research area. It's you can call it optimization via simulation, or you can call it simulation optimization, or for short, SimOpt. And SimOpt has a lot of cool things underneath it. Some of those things are things like metaheuristics, genetic algorithms, ant colony optimization, simulated annealing, taboo search. Some of these things your book at least talks about a little bit in section 12.4. Machine learning is involved in here, neural networks, a lot more stats. There's a lot of cool, interesting research questions. I teach a graduate seminar periodically where we go into some of these metaheuristics for how you can do an automated search through complicated things like simulations that aren't mathematical functions with gradients that you can easily optimize like you would in a calculus class, but sort of outside of the scope of this course. But I want you to know that the field exists, and if you're interested in simulation and all of these sort of statistical peculiarities, then I would encourage you to look into further study into this field of simulation optimization. I think it'll open up a lot of interesting doors. All right, the last thing I want to introduce is a topic called meta-modeling. So far, we've been using simulations as models for real systems, and so instead of tweaking a real system, we build a simulation that we are confident is a good surrogate for that real system, and we tweak the simulation, and then from those tweaks in the simulation, we make recommendations about the real system. Now, if you want to make a lot of tweaks, or if you want to get sort of a really fine-grained understanding of how certain parameters in your simulation affect performance, then you might need to go one step further and build a model of a model. So the idea is, in step 1, we build a good simulation model, a model that we have validated is a very good representation of a real system. And then in step 2, we use a statistical modeling process, like multiple linear regression or generalized linear modeling, to model the simulation model with effectively a simple mathematical function. We basically curve fit. We fit a line, a regression line, for example, or some curve to data that we get out of the simulation model. And that simpler mathematical function is going to be much easier to summarize to our stakeholders, for one, and it'll give us much more insights. Like, so not, we don't just know that system A is better than system B. We can actually go farther and say, oh, I see that as I increase my number of clerks or my number of operators, then these interesting patterns occur in the performance. The performance starts scaling up, but maybe it rounds off, maybe I get diminishing marginal returns. I start getting a more interesting narrative about what's going on in the system by building a model of the model. So the simulation model is basically just there to generate lots of data that I can use to statistically, to fit something statistically to the simulation model that gives me insights about the real system. So the advantages of using this, why can't we just statistically model the real system? We still would end up getting a nice statistical model out. Well, the thing is, we can gather much more data on the simulation, because we can run the simulation much quicker usually than the real system. But on top of that, as you'll see in lectures K1 and K2, there are experiments that I can design with simulations that are impossible design in the real world. I've already sort of hinted with one with the correlated sampling section we talked about earlier in the lecture. In that case, we set the random number seed to be the same on two different simulations, and it had the effect of basically sending in the same stream of customers into two different simulations, an identical stream. It's impossible to do that in the real world. You just simply cannot replay an input like a number of customers arriving. You can get something that comes close, but you never can send the exact same stream of customers through two different systems, especially where those two different systems are effectively at exactly the same time with nothing else changed. Whereas we can do that in simulation. And because we can do that in simulation, then if we apply statistics to that, it enables us to actually get better statistics out. So we can control for variation that in simulation that we cannot control for in the real world. So this is a weird, nuancy thing. Our simulations have variability, just like the real world. So we're not getting rid of the variability in the simulation. We're controlling for sources of variability. We are assigning certain parts of the variability in the output to the input by controlling the input in a way that we cannot control in the real world. And by applying that control, it allows us to slice the variance up so we can get more explanatory power for the aspects of the variance that are truly due to real differences between our two systems. So all of this is impossible in the real world, but it is possible in simulation. And once you use the simulation, you can build really powerful meta models that would just simply not be able to be fit to the real world, because again, you couldn't have done that experimental design in the real world. And you'll see more examples of this as we get into K1 and K2. And that's all that I wanted to talk about for this lecture. So pop back out to Canvas and answer a question or two, and I will see you at the next lecture.